Section: Introduction. In this section, we discuss the advancements in scaling transformer networks to hundreds of billions of parameters, which have led to remarkable few-shot generalization and reasoning capabilities. However, the significant memory and computational demands pose challenges for training and deploying these models outside of large data centers. This has prompted us to explore more efficient designs. We focus on two main areas of efficiency: parameter efficiency, which involves reducing or sharing model weights, and adaptive computation, where we allocate computational resources based on the needs of the task. One effective method for achieving parameter efficiency is layer tying, where we reuse a common set of weights across multiple layers. For adaptive computation, we often use early exiting, allowing the model to stop processing earlier for simpler tasks. Despite progress in these areas, we still lack an architecture that effectively combines both parameter efficiency and adaptive computation. Recursive transformers, which apply the same shared layers multiple times, provide a solid foundation due to their inherent weight sharing. However, previous attempts at dynamic recursion have faced practical challenges, such as needing specialized training or struggling with efficient deployment. As a result, many methods still rely on a fixed-depth recursion, applying the same computation to every token, which limits true adaptability. In our work, we introduce Mixture-of-Recursions, MORE, a framework that fully utilizes the potential of recursive transformers. MORE trains lightweight routers to determine how many times a shared parameter block should be applied to each token based on its specific needs. This dynamic recursion allows for efficient key-value caching, which reduces memory traffic and enhances throughput without requiring additional modifications. MORE achieves three main goals. It ties weights to reduce parameters, routes tokens to minimize unnecessary computations, and caches key values efficiently, all within a single architecture. Conceptually, MORE serves as a pre-training framework for latent space reasoning, enabling non-verbal thinking during token decoding. Unlike other methods that rely on pre-generated prompts, MORE facilitates this reasoning directly as we decode each token. Our routing mechanism also allows for adaptive reasoning, moving beyond the fixed thinking depth seen in previous approaches. In summary, our key contributions include: 1. A unified framework for efficient language modeling through MORE, which combines parameter sharing, token-level adaptive thinking depth, and memory-efficient caching. 2. A dynamic recursion routing system that assigns per-token recursion depths, aligning training with inference and eliminating the need for costly post-hoc routing. 3. Extensive empirical validation showing that MORE improves validation loss and few-shot accuracy across various model sizes. 4. An efficient architecture that significantly reduces training computations by focusing only on essential sequences, while also enhancing inference throughput through reduced cache sizes. We also explore recursive transformers, which use a stack of unique layers to create token representations. Instead of having distinct sets of weights, these models reuse layers across depth, allowing for increased computation without adding to the parameter count. We examine several parameter sharing strategies, including cycle and sequence sharing, which differ in how they reuse layers while maintaining the same effective number of layers. Section Summary. In this section, we introduce Mixture-of-Recursions, MORE, a novel framework that unifies parameter efficiency and adaptive computation in recursive transformers by dynamically assigning token-specific recursion depths and implementing efficient key-value caching. Our approach significantly enhances language modeling efficiency, reduces computational overhead, and improves performance across various model sizes without the need for complex post-hoc routing methods. Section: Enhanced Training and Inference Efficiency in Recursive Models. In this section, we discuss how we can enhance training and inference efficiency in recursive models. By using parameter sharing strategies, we can significantly reduce the number of unique trainable parameters, which helps manage the model's memory usage. When we look at distributed training, this becomes particularly efficient with fully sharded data parallel, FSDP. Instead of needing one operation for each iteration, A recursive model allows us to reuse gathered parameters across all recursive steps, making it much more efficient. We also introduce a new inference method called continuous depth-wise batching. This approach lets us group tokens at different stages into a single batch since they all use the same set of parameters. This helps eliminate idle waiting times, leading to better throughput. However, we recognize some limitations in previous works. Even though model parameters are shared, each depth typically uses separate key-value caches, which doesn't reduce cache sizes and keeps retrieval delays high. Additionally, many recursive models apply a fixed recursion depth to all tokens, overlooking their varying complexities. While some methods can adapt to this, they often require separate training phases that can hurt performance. Ideally, we want the recursion depth to be learned dynamically during pre-training, allowing the model to adjust based on each token's difficulty. But this introduces a challenge. Tokens that exit early will lack key-value pairs in later recursion depths, necessitating a complex parallel decoding mechanism. To address these issues, we propose Mixture-of-Recursions, MORE, a framework that dynamically adjusts the recursion steps for each token during both pre-training and inference. MORE consists of two main components: a routing mechanism that assigns specific recursion steps to tokens based on their difficulty, and a key-value caching strategy that determines how key-value pairs are stored and used at each recursive step. In our expert choice routing, inspired by top K gating, each recursion depth acts as an expert that selects its preferred top tokens. At each recursion step, the router calculates a score for each token based on its hidden state and routing parameters. The top tokens are then chosen to proceed through the recursion block, ensuring that only selected tokens can be re-evaluated in the next step. This method prioritizes computation for the most challenging tokens. In contrast, our token choice routing commits each token to a full sequence of recursion blocks from the beginning. The router computes a score for each expert, and the token is assigned to the expert with the highest score. We ensure that the routing strategies are comparable by aligning the token allocation budgets of expert choice with those of token choice, calibrating the selection process to maintain balance across recursion depths. This way, we can effectively manage the distribution of tokens across different recursion steps. Section Summary. In this section, we introduce the Mixture-of-Recursions, MORE, framework, which dynamically adjusts recursion steps for each token during pre-training and inference to enhance efficiency and throughput. We also describe two routing strategies, expert choice and token choice, that optimize computation by selectively focusing on more challenging tokens while addressing limitations in existing recursive models, such as high retrieval latency and fixed recursion depths. Section: Strengths and Limitations. Tab: Method_comparison left. In this section, we discuss the strengths and limitations of our approach. While expert choice routing ensures perfect load balancing with static top K selection, it has issues with information leakage. This leakage violates causality during training, requiring us to use an auxiliary router or a regularization loss to accurately identify top K tokens during inference without future token information. On the other hand, token choice avoids this leakage but often needs a balancing loss or loss-free algorithms due to its load balancing difficulties. We will delve deeper into these components for our Mixture-of-Recursions, MORE, model. Next, we address KV caching strategies, specifically recursion-wise caching and recursive sharing. Dynamic depth models often face challenges with KV cache consistency during autoregressive decoding. When a token exits early, its keys and values in deeper layers may be missing, which can be vital for subsequent tokens. Some methods try to reuse outdated entries or run parallel decoding, but these add complexity. Therefore, we designed 2 kV cache strategies for MORE: recursion-wise caching and recursive sharing. In recursion-wise KV caching, we selectively cache key-value pairs, storing them only for tokens routed to a specific recursion step. This means the KV cache size at each recursion depth is determined by the capacity factor in expert choice or the actual balancing ratios in token choice. Attention is focused only on these locally cached tokens, enhancing memory efficiency and reducing input-output demands. For recursive KV sharing, we ensure that all tokens pass through at least the first recursion block. We cache key-value pairs only at this initial step and reuse them in all subsequent recursions. As a result, while the query length may shorten at each recursion depth based on selection capacity, the key and value lengths remain consistent, allowing all tokens to access past context without needing recomputation. Regarding strengths and limitations, recursion-wise caching significantly reduces KV memory and input-output across the model. It also lowers per-layer attention computations, leading to improved efficiency during training and inference. Meanwhile, recursive sharing maximizes memory savings by reusing context globally, allowing for faster processing by skipping certain operations. However, attention computations only decrease slightly, and high KV input-output can still create a decoding bottleneck. In our experiments, we pre-trained our models from scratch using a llama-based transformer architecture, following the configurations of small LM open-source models on a deduplicated subset of the FineWeb-Edu dataset. We evaluated the models on the validation set of FineWeb-Edu and 6 few-shot benchmarks, with detailed procedures outlined in the appendix. Our Moore model outperformed baselines with fewer parameters under the same training compute. With a training budget of 16.5 times 10 to the 18 floating-point operations, we compared Moore against vanilla and recursive transformers. The Moore model, using an expert choice router and 2 recursions, achieved a lower validation loss and higher few-shot accuracy, despite using nearly 50% fewer parameters. This efficiency allows us to process more training tokens within the same budget. As we increase the number of recursions, Moore continues to perform competitively, consistently surpassing recursive baselines while staying close to the full-capacity vanilla model. We also evaluated performance with a fixed number of training tokens. Our Moore model with 2 recursions outperformed both vanilla and recursive baselines, achieving lower validation loss and higher accuracy while using 25% fewer training floating-point operations. This efficiency translates into practical benefits, reducing training time by 19% and peak memory usage by 25%. These gains result from our hierarchical filtering and recursion-wise attention mechanism, which shortens sequence lengths for a better compute accuracy trade-off, even during pre-training. Section Summary. In this section, we discuss the strengths and limitations of our Mixture-of-Recursions, Moore, model, highlighting how expert choice routing ensures load balancing but suffers from information leakage, while token choice avoids this issue but faces load balancing challenges. We also present our KV caching strategies, which enhance memory efficiency and reduce computational overhead, ultimately demonstrating that Moore outperforms baseline models in both training efficiency and accuracy with fewer parameters. Section. Moore performance varies with routing and caching strategies. In this section, we examine how the performance of the mixture of routing, Moore, model changes based on different routing and caching strategies. We also test several design variations within the Moore framework, particularly with 3 routing options, which is lightweight yet comparable to the standard model. We find that using token choice routing results in lower performance at 40% compared to expert choice routing at 42.6%, highlighting the importance of routing granularity on model effectiveness. Additionally, while sharing the key value cache slightly decreases performance compared to independent caching, it enhances memory efficiency, making it a favorable option when memory usage is a priority. Next, we analyze the isoflop, which helps us determine if performance improves as we scale the model and computational resources. We compare Moore with both the standard and recursive transformers across various model sizes and computational budgets to demonstrate that Moore maintains competitive or superior performance as we increase scale. For our experimental setup, we test 4 model sizes: 135 million, 360 million, 730 million, and 1.7 billion parameters, keeping the number of recursions fixed at 3 for both recursive and Moore configurations. This results in about 1/3 the number of unique parameters. Each model is pre-trained under 3 different computational budgets: 2 times 10 to the power of 18, 5 times 10 to the power of 18, and 16.5 times 10 to the power of 18. We find that Moore is a scalable and efficient architecture. As shown in our results, Moore consistently outperforms recursive baselines across all model sizes and computational budgets. Although it performs slightly worse than the standard model at the smallest size due to a recursive capacity limitation, this performance gap quickly narrows as we scale up. For models larger than 360 million parameters, Moore not only matches but often surpasses the standard transformer, especially under lower to mid-range budgets. Overall, these findings indicate that Moore is a strong candidate for both pre-training and large-scale deployment due to its efficient use of parameters. In terms of inference throughput, Moore benefits from a parameter-sharing architecture that allows for continuous depth-wise batching, significantly enhancing throughput compared to standard transformers. This approach ensures high GPU utilization by quickly replacing completed sequences with new tokens during decoding. The early exiting mechanism in Moore further optimizes the computational batch. For our throughput evaluation, we measure performance for 360 million parameter Moore models with recursion depths of 2, 3, and 4, all trained under a budget of 16.5 times 10 to the power of 18 flops. We assess throughput in tokens per second based on the time taken to generate tokens per sample, with the number of tokens drawn from a normal distribution averaging 256, starting without any input prefix. We explore 2 batching configurations: a fixed batch size of 32 and a maximum batch size calculated by multiplying 32 by the ratio of the maximum batch sizes of the standard and Moore models. Our results show that Moore significantly boosts inference throughput with continuous depth-wise batching. Across both batching configurations, all Moore variants outperform the standard model, which also uses continuous sequence-wise batching. Increasing recursion depth leads to more tokens being processed early and reduces key-value cache usage, further enhancing throughput. For instance, Moore with a recursion depth of 4 achieves up to a 2.06 times speedup with maximum batch size. While there is a slight drop in performance, this trade-off is beneficial given the substantial increase in throughput. We also identify that the middle cycle parameter sharing strategy is the most effective. We empirically compare 4 strategies: cycle, sequence, middle cycle, and middle sequence, on recursive transformers with model sizes of 135 million and 360 million. Our findings show that middle cycle consistently results in the lowest validation loss, confirming its effectiveness. Finally, we conduct an extensive study to understand the impact of various design choices within the expert choice and token choice routing schemes in our Moore framework. In the expert choice routing setup, we evaluate several design aspects, including solutions to mitigate causality violations, normalization functions, router architectures, and the effect of an auxiliary loss. Our key findings indicate that using an auxiliary loss is more effective for inference than training a separate auxiliary router, and that a sigmoid normalization function combined with a simple linear router architecture yields the best performance. The auxiliary loss has a minor effect on accuracy but slightly reduces the number of unused tokens. Section Summary. In this section, we evaluate the performance of the Moore framework with different routing and caching strategies, finding that expert choice routing outperforms token choice routing and that KV cache sharing improves memory efficiency despite a slight performance drop. We also demonstrate that Moore maintains competitive performance across various model sizes and compute budgets, significantly boosts inference throughput through continuous depth-wise batching, and identify the middle cycle as the most effective parameter sharing strategy for our models. Section. In token choice routing, balancing loss yields stable and accurate routing. In this section, we explore token choice routing, where balancing loss leads to stable and accurate routing. For our token choice routing, we adopt standard practices in Mixture of Experts, MO, and enable Z-loss by default. We compare 2 strategies, one that uses a balancing loss and another that trains without loss using router bias. Both methods yield similar log probability and few-shot accuracy, but the balancing loss significantly reduces max VO in our more architectures, making it the better option for stability. However, we notice that the model often struggles to balance loads among different experts for almost half of the training steps. We find that using softmax activation with an MLP router performs best, and while removing Z-loss improves performance and stability, we reintroduce it with a small coefficient in the final design. Next, we examine KV sharing in vanilla and recursive transformers. Our findings align with previous research, showing that when we pre-train models from scratch, KV sharing does not usually hurt performance due to increased parameter flexibility. Interestingly, the recursive transformer remains robust to KV sharing, even with fewer degrees of freedom. We support this by analyzing KV pairs at each recursion depth, revealing consistent magnitude patterns and high similarity, which explains the minimal performance drop from KV sharing. We also compare recursion-wise KV caching and recursive KV sharing in our More framework. We observe that while recursive KV sharing reduces memory usage and overall computations, it significantly degrades performance in expert choice routing under fixed token settings. This suggests that focusing on tokens active at that recursion depth may be more advantageous. In contrast, More with token choice routing benefits from KV sharing, as the additional context from shared KV pairs can help improve its less accurate routing decisions. Regarding More scaling, we illustrate that it shows a unique compute optimal scaling behavior compared to baselines under ISO flops constraints. The steeper slope of More's optimal path indicates it benefits more from increasing parameter counts rather than additional data. Thus, the best scaling strategy for More models is to invest in larger models trained for shorter durations. We also discuss how recursion depth reflects the semantic importance of tokens. In our qualitative example, we see that content-rich tokens like people and drugs go through 3 recursion steps, while function words pass through 2, and moderately important words typically undergo just 1. This pattern suggests that recursion depth allocation closely aligns with the semantic significance of each token. Furthermore, we find that the expert choice router with auxiliary loss effectively separates selected from unselected tokens. Our visualizations show that at each recursion step, the routing scores for selected tokens cluster around 1, while unselected tokens cluster near 0, demonstrating perfect separation. Lastly, we visualize how log likelihood changes across recursion steps in More models with varying maximum recursion depths. Our results indicate that deeper recursion not only enhances computation but also allows each step to refine token representation, leading to improved performance. This supports the idea that More enables test time scaling, where allocating more recursion steps during inference can enhance generation quality. In summary, we highlight that parameter sharing offers a different route to efficiency. The universal transformer demonstrated that applying a single block repeatedly can match the power of deeper, non-shared stacks. Loop transformers have proven effective in various tasks, and by incorporating low-rank adaptation in each loop, we achieve relaxed recursive transformers. Recent studies show that recursive transformers excel in latent reasoning through recurrent depth, and varying the number of recursions per input can optimize compute allocation during training and inference. Section Summary. In this section, we explore token choice routing in Mixture-of-Experts, More, models, highlighting that using a balancing loss leads to more stable routing compared to loss-free methods, despite challenges in load balancing among experts. We also discuss the benefits of key value, KV, sharing for token choice routing, the optimal scaling behavior of More favoring model size over training length, and how recursion depth allocation reflects the semantic importance of tokens, ultimately enabling improved performance through deeper recursion at test time. Section: Adaptive Computation. In this section, we discuss adaptive computation and its benefits in reducing training and inference costs across various models, from traditional neural networks to large language models. We note that early exiting methods allow us to stop processing easier samples by skipping some layers. Additionally, we can combine early exits with speculative decoding to speed up inference by using lower layers for quick drafts. We introduce the mixture of depths (MOD) approach, which treats adaptive depth as a routing problem. Here, a router at each layer chooses which tokens will undergo full computation while others bypass the layer, allowing for more precise computation allocation. This method is particularly effective for transformer architectures and has been adapted for other types of models, demonstrating a promising way to manage computation at the token level. We also explore the routing mechanism in large language models, LLMs, which increasingly use routers for adaptive computation, especially in sparse mixture-of-experts (MO) frameworks. In these frameworks, each token is processed by a selected group of expert networks, significantly enhancing model capacity without adding computational burden. Early MO designs used a token choice strategy, where the router picked the top experts based on the token's hidden state. However, this often caused load imbalances among experts, leading to the need for balancing losses. To improve this, expert choice routing was introduced, allowing each expert to choose which tokens to process, ensuring balanced workloads. We then address key value (KV) caching, which stores key and value tensors for each token during decoding. This reuse helps avoid time-consuming recomputation and increases throughput. However, keeping these tensors can quickly fill GPU memory, especially with long contexts and large batches. Previous solutions included quantizing KV activations, discarding less important entries, and sharing keys and values across attention heads. We propose further improvements by allowing adjacent layers to share the same tensors, which saves memory without significantly affecting quality. Our mixture-of-recursions (MORE) approach suggests that KV caches from early recursions can be reused later, potentially lowering memory use even more and speeding up processing for prompts over 1 million tokens. Lastly, we highlight the emerging trend of enabling LLMs to reason internally within hidden states instead of relying solely on verbalization. Some methods use fixed latent reasoning depths with special tokens or structured prompts to guide the model through a set number of reasoning passes. Others create a feedback loop by reusing hidden states to simulate a chain of thought. While these methods enhance reasoning, they often lack the flexibility to allocate computation effectively, leading to inefficiencies. We believe our MORE framework can bridge the gap between adaptive computation and latent reasoning, enhancing the model's reasoning capabilities.